I mean, string theory proposes the wrong number of dimensions of space, for instance. It proposes the wrong sign for the cosmological constant, for instance. All sorts of things which have come out of string theory are just wrong. Now, you could get round this one way or another. I know people like to tuck all these extra dimensions into a little tiny ball. They haven't answered the question that I've often raised in my books about that, which is that it doesn't really solve the problem. I mean, there are big, huge problems facing string theory. I don't quite know why we're talking about this with the multiverse anyway, because string theory is a particular theory which I don't think has much in the way of support for it. It's got a lot of people who argue for it, but that's not scientific support. There aren't experiments which support string theory. Conformal Cyclic Cosmology, or CCC as I sometimes call it, is a cosmological scheme which I introduced in about 2005, sometime around then, which has, I talk about things which are called eons. Now, our present eon would be starting with the Big Bang, the universe expands, and then it goes into this exponential expansion, which is fairly recently observed, and then that goes on forever. This remote expansion is physically equivalent to another Big Bang. And our Big Bang was the continuation of the remote future of an exponentially expanding previous eon. And the idea is that these eons go on and on and on forever in both directions.
The quest to unravel the mysteries of the universe has been an enduring pursuit of humanity for centuries. From ancient civilizations gazing at the stars in wonder to the most advanced scientific endeavors of today, the desire to understand the true nature of reality has driven us to explore various theories and models. In the realm of modern physics, two prominent theories, string theory and Roger Penrose's Conformal Cyclic Cosmology, CCC, theory, have captured the imagination of scientists and theorists alike. Each theory offers a unique perspective on the fundamental forces and particles that govern the universe. And they come with their own set of strengths, weaknesses, and complexities. String theory, often described as the theory of everything, is a theoretical framework that seeks to provide a unified description of the universe's fundamental forces and particles. At its core, string theory posits that the basic building blocks of the universe are not point-like particles, as described in traditional particle physics, but rather tiny vibrating strings. These strings can oscillate at different frequencies, giving rise to the various types of particles and interactions we observe in the universe. String theory emerged in the late 20th century as a response to the challenge of reconciling two seemingly incompatible theories, general relativity, which explains gravity as the curvature of spacetime on cosmic scales, and quantum mechanics, which deals with the behavior of matter and energy on subatomic scales. One of the remarkable features of string theory is its ability to seamlessly integrate gravity into its framework. Unlike other quantum field theories where gravity is often treated as an external force acting on particles, string theory directly incorporates the gravitational force into its equations. This integration represents a significant departure from previous attempts to unify quantum mechanics and gravity and has garnered substantial attention in the scientific community. Moreover, string theory introduces the concept of various string vibrational modes, each corresponding to different types of particles. For instance, particles like quarks, electrons, and photons, which constitute the standard model of particle physics, can be interpreted as distinct vibrational states of these fundamental strings. This insight potentially provides an explanation for the diverse spectrum of particles observed in particle accelerators, offering a unified perspective connecting the fundamental forces of the universe with the vibrational patterns of these strings. It is this unique and compelling approach that makes string theory a contender in the quest to understand the underlying nature of our reality. However, it is important to acknowledge that string theory is not without its challenges and skeptics. A prominent figure in the scientific community, who has expressed skepticism about string theory, is the renowned British mathematician and Nobel Prize laureate, Sir Roger Penrose. Penrose, celebrated for his contributions to general relativity, cosmology, and black hole studies, holds the view that string theory is incorrect and that there are no additional dimensions in our universe. His skepticism is rooted in both conceptual and empirical concerns. One of Penrose's central criticisms of string theory is its lack of predictive power and empirical testability. According to him, a fundamental theory of physics should not only be mathematically elegant and internally consistent but should also generate testable predictions that can be verified or disproven through experiments or observations. This emphasis on empirical testability is a crucial criterion for the credibility of any scientific theory, and Penrose believes that string theory falls short in this regard. Despite its remarkable mathematical beauty, string theory has not yet produced concrete predictions that can be directly tested using current or foreseeable experimental techniques. Penrose also raises concerns about the vast landscape of possible solutions in string theory. This vastness makes it challenging to pinpoint a unique prediction that distinctly sets string theory apart from other scientific frameworks. The lack of specificity diminishes the theory's scientific value, and from Penrose's perspective, it hampers its ability to offer concrete predictions regarding the behaviors of particles or the outcomes of experiments. Furthermore, Sir Roger Penrose's skepticism isn't limited to string theory, it extends to the fundamental nature of spacetime and geometry. His favored alternative, Twistor theory, emphasizes the geometric properties of spacetime and the relationships between light rays and null geodesics. Penrose argues that string theory overly emphasizes particle-like entities and their vibrations, potentially neglecting the deeper geometric structure of spacetime. In his view, a more geometric approach, exemplified by Twistor theory, has the potential to provide a deeper understanding of the fundamental nature of the universe. In addition to his critiques of string theory, Penrose has introduced an alternative cosmological model called Conformal Cyclic Cosmology, CCC. This model deviates from the widely accepted inflationary Big Bang theory and presents a distinctive view of the universe's ultimate destiny. CCC proposes that the universe experiences an endless series of cycles, each initiated by a Big Bang and seamlessly transitioning into the next without the occurrence of a singular point or a big crunch. At the heart of CCC is conformal geometry, a mathematical transformation that maintains angles while altering distances. Penrose's idea is that this transformation preserves information and structures from one eon, passing them to subsequent eons, creating a cyclical pattern in the universe's evolution. CCC's intriguing consequence is the avoidance of the concept of an ultimate Big Crunch singularity, a feature of traditional cosmological models. Penrose's skepticism even extends to the existence of dark matter, often used to explain gravitational effects in galaxies. While he doesn't deny unseen mass, he proposes an alternative explanation within CCC. Penrose suggests that some gravitational anomalies attributed to dark matter may result from the cumulative influence of gravitational radiation emitted by distant massive objects over cosmic time scales. Choosing between string theory and Penrose's CCC theory often boils down to personal and philosophical preferences. String theory appeals to those who value mathematical elegance and unifying fundamental forces, while CCC theory is favored by those who seek a more intuitive, geometric approach and wish to avoid the concept of a cosmic singularity. It highlights the diversity of thought in the scientific community. The ongoing debate between string theory and CCC theory lacks conclusive experimental support. Scientists are actively researching and testing these frameworks. The verdict on which theory is more plausible may only emerge with new empirical evidence or a more comprehensive theory. In our quest to understand the universe, answers remain just out of reach, underscoring the complex nature of this scientific pursuit. Thank you for watching another episode of Elizib. While you are still here, don't forget to like and subscribe.